Let's begin with something very simple, something you can always see. Something solid. Look at your right hand. Don't be shy, go ahead. If your eyes are closed, open them for just a moment. Look at your right hand in whatever dim light surrounds you. See the skin, the lines across your palm, the subtle variations in color. See your fingernails, your knuckles, the way your fingers curve naturally even when relaxed. Your hand looks solid, doesn't it? It looks like a thing, a discrete object with clear boundaries, with substance, with weight and texture, and definite position in space. Okay, now close your eyes again. And now, let me tell you what your hand actually is. Your hand is mostly empty space, vast, incomprehensible emptiness. If an atom were the size of a football stadium, the nucleus would be a marble at the center of the field, and the electrons would be little tiny specks orbiting somewhere in the upper deck. Everything in between, the entire volume of the stadium, would be literally nothing. Void, absence. Your hand contains approximately 7 octillion atoms. That's 7 followed by 27 zeros, and each of those atoms is 99.99999999999% empty space. So when you press your hand against a wall, when you feel the solid resistance, you're not actually touching anything. The electrons in your hand and the electrons in the wall are repelling each other through electromagnetic force, creating the sensation of solidity, but there's no actual contact. Just force fields pushing against force fields, emptiness pushing against emptiness. But it gets stranger, much stranger, because even that marble-sized nucleus, even that tiny speck of an electron, they're not really things at all. Let's descend deeper. Let's go down into the subatomic realm, into the quantum world, where the rules change, where reality becomes something else entirely. The particle that isn't. Imagine you're standing at the edge of an ocean. Not a real ocean, a quantum ocean. The water is perfectly still, perfectly smooth, stretching to the horizon in all directions. The surface is like glass, like a mirror reflecting a sky that contains no sun, no stars, just a uniform sourceless light. This ocean is what physicists call the quantum field. It's not made of water, of course. It's not made of anything material. It's pure potential, pure possibility. A substrate of existence from which everything emerges. Now, imagine a single drop of rain falling onto this glassy surface. The drop strikes the water and ripples spread outward. Concentric circles, expanding, overlapping, creating interference patterns where they meet. That ripple, that disturbance in the quantum field, is what we call a particle. An electron is a ripple in the electron field. A photon is a ripple in the electromagnetic field. A quark is a ripple in the quark field. Every particle that exists, every fundamental building block of matter and energy, is nothing more than a vibration, a wave, a disturbance propagating through an underlying field of pure potential. But here's where it becomes strange. That ripple isn't somewhere in the ocean. It doesn't have a location. It's spread out, diffused, existing as a pattern across the entire surface. The ripple is everywhere the wave function extends, which could be the entire universe. The particle doesn't have a position until you measure it, until you look at it, until you interact with it in some way that forces it to collapse from a spread-out wave of possibility into a single, definite point. This isn't a metaphor. This isn't a simplification. This is what quantum mechanics tells us about reality at its most fundamental level. Particles don't have definite properties until they're measured. They exist in what we call a superposition, a state of being multiple things simultaneously. An electron doesn't have a location until you measure its location. It doesn't have a momentum until you measure its momentum. It doesn't even have a definite spin, that quantum property that determines certain behaviors, until you force it to choose. Before measurement, it's all possible locations, all possible momentums, all possible spins. The particle is smeared across space and time, existing as a probability distribution, a wave function that describes where and what it might be when you finally look. Schrödinger, one of the founding fathers of quantum mechanics, described this mathematically with his famous equation, the Schrödinger equation, which describes how quantum wave functions evolve over time. But he hated the implications. He spent years trying to prove that particles must have definite properties even when we're not looking, that reality must be real even in the absence of observation. He failed. Every experiment ever conducted supports the strange quantum picture. Particles genuinely don't have definite properties until measured. Reality at the quantum level is not deterministic. It's probabilistic. It's potential. It's a shimmering field of possibilities that only crystallizes into definite actuality when consciousness, or at least some measuring apparatus, intervenes. Let's slow down, take a breath, let that settle. The fundamental building blocks of reality don't have definite properties until observed. This violates everything your experience tells you about the world. The chair you're sitting on seems solid and definite whether you're looking at it or not. The moon appears in the sky regardless of whether anyone is watching. Common sense says that things have properties independent of observation, but common sense is wrong. Or rather, common sense applies to the macroscopic world, the world of chairs and moons and human bodies, but it breaks down completely when you examine the substrate, the underlying quantum realm from which the macroscopic world emerges. This is called wave-particle duality, though that name is misleading. It suggests that quantum objects are sometimes waves and sometimes particles, flickering between two states. But that's not quite right. Quantum objects are neither waves nor particles. They're something else, something our language and concepts aren't equipped to describe because we evolved in a macroscopic world where things are solid and definite, where nothing exists in superposition, where observation doesn't change reality. When you're not looking at an electron, it propagates through space as a wave. It spreads out, it diffracts and interferes with itself like ripples on water. Its behavior is described by a wave function, a mathematical object that specifies the probability of finding the electron at various locations if you were to measure it. But when you do measure it, when you set up a detector to see where the electron is, the wave function collapses instantly, discontinuously. The spread-out wave of probability becomes a single definite point. The electron appears somewhere, and the probability of finding it everywhere else drops to zero. This collapse is instantaneous and non-local. It happens faster than light could travel across the wave function's extent. It violates the principle that nothing can travel faster than light, yet it happens every time, in every quantum measurement ever performed. Einstein called this spooky action at a distance, and he didn't mean it as a compliment. He thought it revealed a flaw in quantum theory. He believed there must be hidden variables, deeper deterministic laws that quantum mechanics hadn't yet discovered that would restore sanity to physics. But Einstein was wrong. Tests of Bell's inequalities, mathematical constraints that any theory with hidden variables must satisfy, have shown conclusively that no hidden variable theory can reproduce quantum mechanics predictions. The spookiness is real. The non-locality is real. The instantaneous collapse is real. Reality at the quantum level genuinely doesn't behave the way we think reality should behave. There's another principle, equally disturbing, equally fundamental. It's called the Heisenberg uncertainty principle, and it's often misunderstood. People sometimes think it means we can't measure certain properties precisely because our measuring instruments disturb the system. That if we just built better, more precise detectors, we could overcome the uncertainty. But that's not what it means at all. The uncertainty isn't about measurement limitations, it's about reality itself. Certain pairs of properties, like position and momentum, or energy and time, cannot both have definite values simultaneously. Not because we can't measure them, but because the properties themselves are fundamentally incompatible. If a particle has a definite position, its momentum is completely undefined. It could be anything with equal probability. If a particle has a definite momentum, its position is completely undefined. It's spread out across all of space. Usually, particles exist in some intermediate state, where both position and momentum are somewhat defined, but neither is precise. The more precisely you know one, the less precisely you can know the other. Not because of measurement limitations, but because the universe itself doesn't allow both properties to be definite simultaneously. Think about that. The universe doesn't allow it. Reality has built-in limits on what can be simultaneously true. There are questions you can ask about a particle, perfectly reasonable, sensible questions like, where is it and how fast is it moving, that have no answer. Not because we don't know the answer, but because there is no answer to know. The particle doesn't have a simultaneous definite position and momentum. The universe doesn't contain that information. Reality itself is uncertain, fuzzy, indeterminate at the quantum level. This isn't ignorance. This is the fundamental nature of existence. Let's go deeper still. Let's examine what a quantum particle actually is when we're not measuring it. The mathematics of quantum mechanics describes particles using wave functions, usually denoted by the Greek letter psi, shear. The wave function is a complex-valued function defined over space and time. At each point in space and each moment in time, the wave function has a value, a complex number with both magnitude and phase. The magnitude of the wave function at a particular location tells you the probability amplitude for finding the particle there if you measure its position. Square that amplitude and you get the actual probability. But here's the thing, the wave function itself isn't a physical wave. It's not made of anything. It doesn't exist in real three-dimensional space the way water waves or sound waves do. The wave function exists in what's called Hilbert space, an abstract, infinite-dimensional mathematical space where each dimension represents a possible state the system could be in. When physicists say a particle is its wave function, they're saying something deeply strange. They're saying the particle doesn't have a definite actual state. Instead, it exists as a superposition, a weighted sum of all possible states, each with its own probability amplitude. An electron in an atom doesn't orbit the nucleus the way Earth orbits the Sun. It exists in an orbital, a probability cloud surrounding the nucleus, a three-dimensional region where the electron might be found if you measure its position, but isn't actually definitely at any particular location when you're not measuring. The electron is the cloud is the electron. They're the same thing. The electron is a spread-out wave of probability, existing in multiple places simultaneously, being everywhere and nowhere until the moment of measurement collapses the wave function and forces it to choose. Breathe. Let that sink in. The most fundamental constituents of reality don't have definite properties or locations. They exist in superposition, being multiple contradictory things at once, until observation forces them to become definite. If we could see at the quantum level, if we could somehow perceive reality at the scale of atoms and subatomic particles, what would we see? Not the solid, stable world we experience, not the world of definite objects with clear boundaries. We would see something like a dream, a flickering, shimmering chaos where particles blink in and out of existence, where the vacuum itself, empty space, is not empty but seething with activity, where virtual particles spontaneously appear in particle-antiparticle pairs, exist for tiny fractions of a second, then annihilate each other and disappear. This is called quantum foam or space-time foam. At the smallest scales, around the Planck length, which is about 10 circumflex 35 meters, far smaller than any particle we can detect, space and time themselves become uncertain, granular, probabilistic. The smooth fabric of space-time that Einstein described as just an approximation, an average. A macroscopic appearance, zoom in far enough and space-time dissolves into a roiling quantum chaos where the very concepts of distance and duration become fuzzy and ill-defined. Energy and matter flicker into existence from the vacuum, borrowing energy from the uncertainty principle, which allows violations of energy conservation for brief moments, as long as the violation times the duration is less than Planck's constant. We can detect the effects of these virtual particles. They contribute to the anomalous magnetic moment of the electron. They cause the Casimir effect, where two metal plates in a vacuum experience an attractive force because fewer virtual particles can exist between the plates than outside them. They cause the Lamb shift, a tiny difference in energy levels of hydrogen that wouldn't exist if the vacuum were truly empty. The vacuum is not empty. Reality at its foundation is not static. The quantum realm is alive, dynamic, constantly fluctuating, never at rest. And you are made of this. Your atoms, your molecules, your cells, they're all composed of quantum particles obeying these strange rules, existing in superposition, tunneling through barriers, entangling with each other across space, emerging from and dissolving back into the quantum foam. So why don't you experience superposition? Why don't you exist in multiple places at once, or find yourself tunneling through walls or spontaneously vanishing into the vacuum? This is one of the deepest mysteries in quantum mechanics. It's called the measurement problem, or the quantum to classical transition, and despite a century of research, we still don't fully understand it. Somehow, when quantum systems become large and complex, when they interact with their environment in certain ways, the superposition collapses, the wave function decoheres, the quantum probabilities resolve into definite classical outcomes. This process is called decoherence, And it happens incredibly quickly for macroscopic objects. The larger and warmer an object is, and the more it interacts with its surroundings, the faster decoherence occurs. For a single atom in isolation, quantum coherence, the ability to exist in superposition, can persist for seconds or even minutes. For a molecule with 100 atoms, coherence might last microseconds. For a dust grain with trillions of atoms, coherence lasts nanoseconds or less. For a human body with 10 circumflex 28 atoms, constantly interacting with light and air molecules and thermal vibrations, decoherence is effectively instantaneous. This is why you don't experience quantum weirdness directly. By the time quantum systems scale up to the size and complexity of human experience, the weirdness has decohered away, leaving behind the definite classical world we're familiar with. But, and this is crucial, decoherence doesn't solve the measurement problem. It explains why we don't see macroscopic superpositions. But it doesn't explain how or why the wave function collapses, how the universe chooses which possibility becomes actual. Some physicists believe consciousness plays a role, that the wave function collapses when observed by a conscious mind. Others believe in the many worlds interpretation, where the wave function never collapses, and every quantum possibility actually occurs in a separate branch of reality, creating an infinite multiverse where every possible outcome is realized somewhere. Still others believe the Copenhagen interpretation, which essentially says, don't ask what happens during collapse, just calculate the probabilities and make predictions. We don't know. After a century of quantum mechanics, after thousands of experiments confirming its predictions with extraordinary precision, we still don't understand what the theory is actually telling us about the nature of reality. We know how to use quantum mechanics. We know how to calculate. We know how to predict. We've built lasers and transistors and MRI machines and atomic clocks based on quantum principles. We've harnessed the quantum realm for practical purposes. But we don't know what it means. We don't know what really happens when a measurement occurs. We don't know where the boundary between quantum and classical lies, or if such a boundary even exists. Let's pause, take a breath, feel the weight of your body, feel the surface beneath you, feel the air moving gently in and out of your lungs. All of this, the feeling of solidity, the sensation of definite position, the experience of being a singular entity in a definite location, is an emergent property. It's what happens when trillions upon trillions of quantum particles decohere together, when their individual quantum superpositions collapse or average out into something that looks and feels classical, but underneath at the foundation, reality is still quantum. The particles that compose you still exist in superposition when not measured. They still tunnel through barriers, though the probability becomes vanishingly small for macroscopic distances. They're still entangled with particles in their environment, their fates correlated in ways that transcend space and time. You are a quantum system pretending to be classical. You are a wave function that has decohered so thoroughly that you experience yourself as definite, as localized, as real in the conventional sense. But that's not what you are at the fundamental level. At the fundamental level, you're a pattern of quantum probabilities, a wave in the quantum field, a temporary configuration of particles that are themselves not particles at all but excitations in underlying fields. You are, in a very real sense, made of nothing, made of mathematics, made of possibility, made of the same quantum foam from which everything emerges and to which everything returns. Does this make you feel less real? Or does it make reality itself seem more mysterious, more profound, more worthy of wonder? As you drift towards sleep, as your conscious mind begins to dissolve into the dream state, consider this. The boundary between waking and sleeping, between consciousness and unconsciousness, might be a macroscopic echo of the quantum measurement problem. When you're awake, observing, measuring, interacting with the world, the wave function of your experience collapses into definite perceptions. When you sleep, when observation ceases, does your personal wave function spread out again? Do you exist in superposition, experiencing all possible dreams simultaneously until morning comes, and consciousness returns to collapse the possibilities into a single remembered narrative? We don't know. These are not questions quantum mechanics can yet answer. These are mysteries that sit at the boundary between physics and philosophy, between science and consciousness, between what we can measure and what we can only wonder about. But we've only just begun. We've descended from the familiar macroscopic world into the quantum realm. We've seen that particles aren't particles, that reality is uncertain, that observation changes what is observed, In the chapters ahead, we'll go deeper still. We'll examine the experiments that revealed these strange truths. We'll confront paradoxes that challenge the very concept of reality. We'll explore the implications of quantum mechanics for space, time, causality, and consciousness itself. But for now, rest. Let the quantum ocean lap at the shores of your mind. Let the certainty of the waking world dissolve, just a little, into the probabilistic haze of the quantum realm. You're beginning to see beneath the surface, beginning to understand that the world is not what it seems, beginning to perceive the strange, beautiful, disturbing truth that lies at the foundation of existence. And we've only just begun the descent. Sleep now, if sleep comes. Dream, if dreams come. And know that somewhere in the quantum foam, in the substrate beneath reality, your particles are dancing, your wave function is evolving, your quantum state is entangled with the rest of the universe in ways we're only beginning to understand. The quantum realm awaits. And it's far stranger than anyone imagined. There is an experiment, a simple experiment, so simple that high school students perform it in physics classes around the world. So simple that it requires nothing more than a light source, a barrier with 2 slits cut into it, and a screen to catch the light that passes through. And yet this simple experiment reveals something so profoundly disturbing about the nature of reality that Richard Feynman, one of the greatest physicists of the 20th century, called it a phenomenon which is impossible, absolutely impossible to explain in any classical way, and which has in it the heart of quantum mechanics. In reality, it contains the only mystery. Everything strange about quantum mechanics, every paradox, every violation of common sense, every challenge to our understanding of what real means, it's all contained in this one simple experiment. Let's perform it together, slowly, carefully, paying attention to every detail. Because by the time we're finished, you'll understand why physicists have spent a century arguing about what it means, why it drove some of the brightest minds to despair, why it suggests that reality itself depends on observation in ways that seem impossible. Imagine a dark room, perfectly dark, no light at all. Your eyes have adjusted, but there's nothing to see, just blackness. Now imagine a wall in front of you, a barrier, completely opaque. Light cannot pass through it. But in this barrier there are 2 narrow slits, 2 thin vertical openings, perhaps a millimetre wide, separated by a small distance. Maybe a few millimetres. Maybe a centimetre. The exact distance doesn't matter for our purposes. Behind this barrier, several feet away, there's a screen, a detector, something that will record where light hits it when light passes through the slits. Now we turn on a light source. Something that emits a single wavelength of light, perhaps a laser, perhaps a sodium lamp, something coherent, something pure. The light travels toward the barrier. Some of it hits the opaque parts and is absorbed or reflected. But some of it, the light that happens to be traveling in the right direction, passes through the 2 slits. What do you expect to see on the screen behind the barrier? If you're thinking classically, if you're using common sense, you'd expect to see 2 bright bands on the screen, one behind each slit, 2 bright lines corresponding to the 2 openings where light passed through. But that's not what happens. Instead, you see a pattern, an interference pattern. Multiple bright and dark bands across the screen. Bright, dark, bright, dark, bright, alternating stripes of light and shadow. This is strange, but it's explainable. Light is a wave after all. When waves pass through 2 openings, they spread out, they diffract, and then they overlap. Where 2 wave peaks meet, they reinforce each other. Where a peak meets a trough, they cancel out. The bright bands on the screen are places where light waves from both slits arrived in phase, peak meeting peak, creating constructive interference. The dark bands are places where light waves from the 2 slits arrived out of phase, peak meeting trough, creating destructive interference. This is basic wave behavior. Water waves do it. Sound waves do it. Light waves do it. There's nothing mysterious here, nothing quantum, nothing strange. The interference pattern proves that light is a wave. This was demonstrated by Thomas Young in 1801, and it settled a long-standing debate about whether light was made of particles, as Newton believed, or waves, as Huygens believed. Light is a wave. The double-slit experiment proves it. Except, now let's modify the experiment. Instead of using a bright light source, let's dim it way down. Let's reduce the intensity so much that only one photon, one quantum of light, passes through the apparatus at a time. We record where it hits, then we wait for the next photon, record where it hits, then the next, and the next. Each individual photon arrives at the screen as a single point of light, a single dot, a localized impact, like a particle hitting a target. If light were purely a wave, we wouldn't see discrete impacts. We'd see a continuous, spread-out pattern gradually building up, but we don't. We see individual dots. Each photon behaves like a particle when it arrives at the screen. But here's the strange part. As we accumulate thousands of these single photon impacts, as the dots pile up on the screen, they don't form two bright bands behind the slits. They form the interference pattern, the same alternating bright and dark bands we saw with the bright light source. The interference pattern emerges even when only one photon is in the apparatus at a time. Stop. Think about what this means. An interference pattern requires two waves overlapping. It requires something going through both slits simultaneously, so that the waves can meet and interfere with each other. But there's only one photon, a single indivisible quantum of light. It can't split in half. It can't go through both slits. Can it? Apparently it can. Or rather it does. Somehow, in some sense, when a single photon travels toward the barrier with two slits, it doesn't choose one slit or the other. It goes through both. It exists in a superposition of states, going through the left slit and going through the right slit simultaneously. The photon interferes with itself. The wave function associated with the photon passes through both slits, and these two parts of the wave function overlap on the far side of the barrier, creating the interference pattern. Each photon is more likely to arrive at locations where the wave function's two parts constructively interfere, and less likely to arrive at locations where they destructively interfere. But we can't predict where any individual photon will land. We can only calculate probabilities. Over time, as many photons pass through the apparatus one by one, the probability distribution becomes visible. The interference pattern emerges, the pattern that should be impossible for particles, the pattern that proves each photon goes through both slits simultaneously. The photon is a wave when it travels. It's a particle when it arrives. It's both. It's neither. It's something our language can't properly describe. This is already strange, already counterintuitive, already a challenge to common sense. But now we make it worse. Now we try to see which slit the photon actually goes through. We place detectors at the slits, devices that can tell us whether a photon passes through the left slit or the right slit. We're not trying to disturb the photon. We're just trying to gain information. Just trying to see what's actually happening. We run the experiment again. We send photons through one at a time, and now we record which slit each photon passes through. And the interference pattern disappears completely. The moment we measure which slit the photon goes through, the moment we gain that information, the photon stops going through both slits simultaneously. The superposition collapses. The wave function localizes. The photon goes through one slit or the other, not both. And now, when we look at the screen behind the barrier, we see exactly what classical intuition predicted. Two bright bands, one behind each slit. No interference pattern, just the pattern you'd get if photons were classical particles that travel through one slit or the other. The act of observation changes the result, not because the detectors physically disturb the photons, though that's what many people think, but because the act of measurement, the act of gaining information about which path the photon took, fundamentally changes what the photon is. When we don't look, the photon exists in superposition. It takes both paths. Its wave function passes through both slits. It interferes with itself. We get the interference pattern. When we do look, when we measure which slit it goes through, the superposition collapses. The photon takes one definite path. There's nothing to interfere with. We get the classical two-band pattern. Observation, mere observation, the simple act of knowing, changes reality. Perhaps you're thinking, maybe the photon knows we're going to measure it. Maybe the presence of the detectors at the slits causes the photon to behave differently even before the measurement happens. But quantum mechanics is stranger than that. John Wheeler, another brilliant physicist, proposed a variation called the delayed choice experiment. Here's how it works. We set up the double slit apparatus as before. We send a photon toward the slits, The photon passes through, existing in superposition, going through both slits simultaneously, its wave function spreading out on the far side of the barrier. But we don't place the screen in a fixed position. Instead, we wait. We wait until after the photon has passed through the slits, after it's committed to whichever path or paths it's taking, and then we make a choice. We can choose to set up the screen in a way that detects the interference pattern, the pattern that would prove the photon went through both slits. Or we can choose to set up detectors that determine which slit the photon went through, which would collapse the superposition and erase the interference pattern. We make this choice after the photon has already passed through the slits, after the moment when, classically, the photon should have decided whether to go through one slit or both. What happens? The result depends on our choice. If we choose to look for interference, we find it. If we choose to measure which path the photon took, the interference disappears and we find a definite path. Our choice, made in the present, determines what the photon did in the past. This has been experimentally verified, not just with photons traveling a few meters, but with photons that have traveled millions of years across space. Light from distant quasars, separated by gravitational lensing so that it takes two different paths to reach Earth, we can choose billions of years after the light left its source whether to detect which path it took or to look for interference between the paths. And the result of our measurement here and now determines what the photon did billions of years ago. The past is not fixed, it's not determined. It exists in superposition until we measure it, and our measurement collapses not just the future, but the past as well. Causality, the idea that past events determine future events, becomes questionable at the quantum level. Time itself becomes negotiable. Let's think more carefully about what's happening here. Why does measuring which slit the photon goes through destroy the interference pattern? The key concept is called which-way information. If there's any way, in principle, to determine which path the photon took, even if we don't actually look at the data, the interference pattern disappears. It's not about the physical disturbance from the measurement apparatus. It's about information, about the possibility of knowing. Imagine we place detectors at the slits, but we don't look at the output. We save the data on a hard drive and lock it away. We never check which slit each photon went through. The interference pattern still disappears. The mere possibility of knowing, even if we never actually look, is enough to collapse the superposition. But now imagine we take the hard drive containing the which-way information and destroy it. We completely erase any record of which path each photon took. We make it impossible, even in principle, to determine which slit the photon went through. The interference pattern returns. Retroactively, we restore the quantum coherence by erasing the information, even after the photon has long since hit the screen. This is called the quantum eraser experiment, and it's been performed many times with many variations. The results are always the same. If which-way information exists, no interference. If which-way information is erased, interference returns. What matters is not the physical interaction between the measurement device and the photon. What matters is information. What can be known, what is recorded, what leaves a mark on the universe that could, in principle, be read. Quantum mechanics is telling us something profound about the relationship between information and reality. It's suggesting that reality itself, what is actual versus what is merely potential, depends on what information exists, what can be known, what has left an indelible record. Let's approach this from a different angle. Imagine a coin that's truly quantum. Not a regular coin, which is heads or tails even when you're not looking at it, but a coin that exists in superposition, simultaneously heads and tails, until observed. Before you look, the coin is both. The wave function describing the coin contains both possibilities with equal amplitude. The coin has no definite state. It's not that you don't know which it is, it's that it isn't either one. It's both. And neither. It's a superposition. When you observe the coin, the wave function collapses. The superposition resolves into one definite state. The coin becomes heads or tails, 50-50 probability for each outcome. Now imagine two quantum coins prepared in a special entangled state such that they're always opposite. If one is heads, the other is tails. If one is tails, the other is heads. But until you measure them, both coins are in superposition, simultaneously heads and tails. You take one coin to New York, I take the other to Tokyo. We're separated by thousands of miles. You measure your coin. The wave function collapses. Your coin becomes, say, heads. At that instant, that exact instant, my coin, thousands of miles away, becomes tails. Not because any signal traveled from your coin to mine, not because they're connected by some hidden mechanism, but because they share a single quantum state, a single wave function that describes both coins together. Your measurement doesn't just collapse your coin's state, it collapses the entire shared wave function, determining both outcomes simultaneously. This is quantum entanglement, which we'll explore more deeply in later chapters. But it's relevant here because it illustrates something crucial. Quantum mechanics is non-local. What happens here can instantly affect what happens there, with no signal traveling between them. The double-slit experiment contains this same non-locality. When you measure which slit the photon goes through, you're not just gaining information about the photon's location, you're collapsing a wave function that extends through both slits, that is spread across space that describes the photon's state across an extended region. The collapse happens everywhere simultaneously. The interference pattern disappears across the entire screen, not just at the point where the photon hits. The measurement at the slit affects the probabilities at the screen instantly, even though the photon hasn't reached the screen yet. Double-slit experiment was first performed with light. But it works with anything. Electrons. Fire electrons one at a time at a barrier with two slits, and you get an interference pattern. Each electron goes through both slits simultaneously. Each electron interferes with itself. Neutrons. Same result. Interference pattern. Wave-particle duality. Atoms. Even entire atoms. Complex composite objects made of protons, neutrons, and electrons exhibit wave-like behavior. Send atoms through a double-slit apparatus, and they create interference patterns. Each atom exists in superposition, taking both paths simultaneously. Molecules. In 1990, researchers in Vienna performed the double-slit experiment with molecules of C60, buckyballs, spherical molecules containing 60 carbon atoms. Each buckyball has a mass of about 720 atomic mass units. It's not a single particle. It's a complex structure containing 360 protons, 360 neutrons, and 360 electrons, all bound together by electromagnetic forces. And yet, buckyballs create interference patterns. Each buckyball goes through both slits simultaneously. Each buckyball exists in superposition. Each buckyball is a wave. Researchers have since performed the experiment with even larger molecules containing over 800 atoms. Massive, complex structures that by all classical reasoning should behave like definite, localized particles. They don't. They're waves. They interfere. They exist in superposition. Where does it stop? At what scale does quantum behavior give way to classical behavior? When does a system become large enough that it has to be in one place at one time, that it can't exist in superposition? We don't know. That's the measurement problem again. The boundary between quantum and classical is one of the deepest unsolved questions in physics. In principle, there's no limit. The Schrödinger equation applies to systems of any size. A cat can be in superposition. A person can be in superposition. The entire universe can be in superposition. In practice, decoherence happens very quickly for large systems. Interaction with the environment, with air molecules, with photons, with thermal vibrations, causes the quantum coherence to decay, the superposition to collapse, the wave function to decohere into definite classical states. But the transition isn't sharp. There's no specific size or mass or complexity where quantum suddenly becomes classical. It's a gradual process determined by how isolated a system is from its environment. And this raises disturbing questions. If everything is quantum at the fundamental level, if there's no sharp boundary, then is the classical world we experience just an approximation, an emergent phenomenon? A collective decoherence of vast numbers of quantum degrees of freedom? Are we, in some sense, still quantum? Still in superposition, but decohered so thoroughly that we experience ourselves as definite, as localized, as classical. Let's return to the original experiment. A single photon approaching two slits. Before measurement, the photon is a wave. Its wave function passes through both slits. It exists in superposition. It has no definite path. Ask the question, which slit did it go through? And the universe has no answer. The question is meaningless. The photon didn't go through one slit or the other, it went through both. And neither. When you measure which slit it goes through, you're not discovering a pre-existing fact. You're forcing the universe to choose. You're collapsing the wave function. You're creating a definite past where none existed before. The photon doesn't know which slit it goes through before you measure it, but after measurement, it retroactively has gone through one specific slit. The past is created by the measurement. History is written by observation. This seems impossible. It violates everything we think we know about time, causality, the relationship between past and future. But it's true. It's been verified experimentally thousands of times in countless variations. There's no doubt about the observations. The only doubt is about what they mean. Niels Bohr, one of the founding architects of quantum mechanics, took a pragmatic view. He argued that we shouldn't ask what's really happening at the quantum level. We should just calculate probabilities, make predictions, and be content with the fact that the theory works. There is no quantum world, Bohr said. There is only abstract quantum physical description. It is wrong to think that the task of physics is to find out how nature is. Physics concerns what we can say about nature. In other words, don't ask what the photon really does when we're not looking. Just predict what we'll see when we do look. Don't try to create a picture, a visualization, a classical description of quantum events. Just use the math. Calculate, predict, measure, repeat. This became known as the Copenhagen interpretation, and for decades it was the dominant view. Shut up and calculate, as the saying goes. Don't worry about what it means. But many physicists found this unsatisfying. Einstein certainly did. He believed in an objective reality that exists independent of observation. He believed that particles have definite properties even when we're not measuring them. He believed that quantum mechanics, despite its incredible predictive success, was incomplete, a useful approximation that would eventually be replaced by a deeper, deterministic theory. Einstein spent decades searching for that deeper theory. He failed. Every attempt to restore classical determinism, to eliminate the role of observation, to make reality objective again, every such attempt has failed. The universe, it seems, really is quantum. Observation really does create reality. The past really is negotiable, and we have to live with the implications, however disturbing they may be. Take a breath. Feel the air entering your lungs. Each molecule of oxygen, nitrogen, carbon dioxide, each one is a quantum object. Each one exists in superposition when not measured. Each one has a wave function extending across space. The act of breathing is an act of measurement. Your lungs interact with air molecules, collapsing their wave functions, forcing them to have definite positions and momenta. Your body is a measuring apparatus. Consciousness is not required, just physical interaction. But before that interaction, before the air reaches your lungs, each molecule is spread out, is probabilistic, is everywhere and nowhere. You are breathing quantum superpositions, collapsing wave functions with every breath, creating definite reality from quantum possibility, moment by moment, breath by breath. The boundary between you and the world is not as sharp as it seems. You're constantly interacting with quantum systems, constantly causing decoherence, constantly participating in the transition from quantum to classical, from potential to actual. You are not separate from the quantum realm. You are immersed in it, made of it. You are a pattern in the quantum field, a temporary configuration that is decohered enough to seem stable, to seem definite, but which is still at the foundation quantum through and through. Asterisk rest in the mystery. The double-slit experiment is over a century old. We've performed it thousands of times in thousands of variations. We know exactly what happens. We can predict the results with extraordinary precision, and yet we still don't understand what it means. Does observation really create reality? Or does it just reveal a reality that was already determined by hidden variables we can't access? Does the wave function really collapse? Or does the universe split into multiple branches, with each possible outcome realized in a different branch? Is consciousness necessary for measurement, or does any physical interaction count? What exactly is a measurement? Where is the boundary between quantum and classical? Does such a boundary even exist? These questions have no agreed-upon answers. Physicists argue about them, philosophers argue about them. The debates have continued for decades, and show no signs of resolution, but the observations are undeniable. The predictions are confirmed. Quantum mechanics works. It works better than any theory we've ever devised. It's been tested more rigorously than any other scientific theory, and it has never failed. So we're left with a mystery, a profound, beautiful, disturbing mystery. The universe at its foundation doesn't behave the way we think it should. Reality is not what it seems. Observation changes what is observed. The past is not fixed. The future is not determined. And everything exists in superposition until forced to choose. As sleep approaches, as the certainty of waking consciousness dissolves, let yourself rest in this mystery. Let the definite world become indefinite. Let the boundaries soften. Let the wave function of your awareness spread out, diffuse, become probabilistic. You've seen the heart of quantum mechanics. You've confronted the only mystery, and you've learned that reality, at its deepest level, is stranger than any dream, more mysterious than any myth, more profound than any philosophy. The double slit waits in the darkness. The wave passes through. The interference pattern emerges, and the universe reveals, over and over, that it is not what we thought it was. Sleep now. Dream now. And know that the boundary between waking and sleeping, between definite and indefinite, between actual and potential, is thinner than you ever imagined. The quantum realm has claimed you, and you will never see the world the same way again. There is a cat. It sits inside a box. The box is sealed, opaque, soundproof. No information can escape from inside the box to the outside world. No light, no sound, no heat signature, nothing. Inside the box, along with the cat, there is a vial of poison, a hammer poised above the vial, a radioactive atom, and a Geiger counter connected to a mechanism that will trigger the hammer if the atom decays. The radioactive atom has a 50% chance of decaying within an hour. If it decays, the Geiger counter detects it. The hammer falls, the vial breaks, the poison is released, the cat dies. If the atom doesn't decay, nothing happens. The cat lives. We seal the box. We wait 1 hour. We don't open it. We don't peek inside. We gather no information about what has happened. Now, here's the question. Is the cat alive or dead? Your intuition says the cat is definitely one or the other. We just don't know which. The atom either decayed or it didn't. The hammer either fell or it didn't. The cat either died or it lived. Our ignorance doesn't change the fact. Inside the box, reality has already made its choice. But quantum mechanics says something else entirely. Quantum mechanics says the cat is both alive and dead, simultaneously. The atom exists in a superposition of decayed and not decayed. The hammer exists in a superposition of fallen and not fallen. The vial exists in a superposition of broken and intact. And the cat exists in a superposition of alive and dead. Not either alive or dead, we just don't know which, but actually, literally, physically, both, existing in two mutually exclusive states at the same time. A living dead cat. A cat that is neither alive nor dead, and yet both, until we open the box, until we observe, until we measure. Then, and only then, the wave function collapses. The superposition resolves. The cat becomes definitely alive or definitely dead. Our observation doesn't reveal a pre-existing fact. It creates the fact. It forces reality to choose. This is Schrödinger's cat. The most famous thought experiment in quantum mechanics. The one that has haunted popular culture, spawned countless memes, and troubled physicists for nearly a century. Erwin Schrödinger proposed it in 1935, not as a serious prediction, but as a reductio ad absurdum, an attempt to show that quantum mechanics, when applied to everyday objects, leads to ridiculous conclusions. He wanted to demonstrate that the Copenhagen interpretation couldn't be right, that there must be something wrong with a theory that predicts macroscopic objects existing in superposition. He called the idea ridiculous. He later said he regretted ever proposing it, but quantum mechanics didn't care about his intentions. The mathematics of the theory genuinely predicts that the cat is in superposition. There's no escape from the conclusion. If quantum mechanics applies to atoms, and the cat's fate is tied to an atom's behavior, then quantum mechanics applies to the cat. The question isn't whether quantum mechanics predicts this. It does. The question is what it means, and whether we should believe it. Let's slow down. Let's examine this carefully. Because Schrödinger's cat touches on something deep and troubling about the nature of reality, measurement, and the role of consciousness in physics. First, let's be clear about what superposition means. A quantum system in superposition isn't in one state or another with us simply being ignorant of which. That would be a classical mixture, like a coin flip that's already happened, but we haven't looked at the result yet. The coin is definitely heads or definitely tails. We just don't know which. Superposition is different. A quantum system in superposition is genuinely, simultaneously in multiple states. Not one or the other. Both. And the system exhibits properties that would be impossible if it were secretly in one definite state. Remember the double slit experiment. A photon passing through both slits simultaneously creates an interference pattern that would be impossible if the photon actually went through just one slit. The superposition is real. It has observable consequences. It's not just ignorance. The same applies to the radioactive atom in Schrödinger's box. A radioactive atom doesn't decay at a definite moment that we simply haven't observed yet. The decay is a quantum process. The atom exists in a superposition of decayed and not decayed, with the probability of each state evolving according to the Schrödinger equation. We can represent this mathematically. The atom's state is a sum, a superposition, of two basis states, decayed and not decayed. Before measurement, the atom is in the state vertical bar atom equals a vertical bar decayed plus b vertical bar not decayed, where a and b are complex numbers called probability amplitudes. The square of their magnitudes gives the probability of finding the atom in each state upon measurement. After 1 hour, for an atom with a half-life such that there's a 50-50 chance of decay, we have vertical bar atom equals 1 screw 2 vertical bar decayed plus 1 screw 2 vertical bar not decayed equals superposition. But until measured, the atom is both. Genuinely both. Now, the atom is connected to the Geiger counter. The Geiger counter is connected to the hammer. The hammer is positioned above the poison vial. The vial is in the box with the cat. These are all physical systems. They interact. They become entangled. Their quantum states become correlated. If the atom is in superposition, then after the entanglement, the entire system, atom, Geiger counter, hammer, vial, cat, is in superposition. Vertical bar system, vertical bar decayed, triggered, fallen, broken, dead, plus 1, 2 vertical bar not decayed, not triggered, not fallen, intact, alive. The cat is not in a definite state. The cat's fate is quantum mechanically entangled with the atom's state. The cat exists in superposition, alive and dead. This is what the mathematics says. This is the prediction of quantum mechanics, applied consistently and without modification. But it seems absurd. Cats are not quantum objects. They're classical. Macroscopic. Definite. A cat is either alive or dead. There's no middle ground. There's no superposition. There's no both and neither. Is there? The paradox of Schrödinger's cat is really just another version of the measurement problem we've already encountered. When does the superposition collapse? At what point does the quantum system become classical? Does the wave function collapse when the atom decays? No, because we've already said the atom is in superposition. Does it collapse when the Geiger counter detects the decay? But the Geiger counter is just another physical system. It can be in superposition too. Its quantum state becomes entangled with the atom's state. Does it collapse when the hammer falls? When the vial breaks? When the poison reaches the cat? When the cat's neurons stop firing? Or does it collapse only when we open the box and look? Different interpretations of quantum mechanics give different answers. Asterisk, the Copenhagen interpretation says the wave function collapses when a measurement is made by a classical apparatus. But what counts as a classical apparatus? What separates quantum from classical? Where is the boundary? The Copenhagen interpretation doesn't really answer these questions. It just asserts that there is a boundary, somewhere, and that collapse happens when a measurement is made. Many physicists in the Copenhagen tradition would say the collapse happens when we open the box. Until then, the cat is in superposition. Our observation creates the definite outcome. But this seems to give consciousness a special role in physics. It suggests that the universe needs observers to become definite. Before consciousness arose, before life, before Earth, before anything that could observe, was the universe in superposition? Did the Big Bang exist in superposition until something evolved to look at it? This feels wrong. It feels anthropocentric. It suggests that consciousness is fundamental to physics, that minds somehow create reality. Some physicists embrace this view, others find it absurd. Dastics, the many worlds interpretation, offers a different answer. The wave function never collapses. Everything that can happen does happen. When we open the box, the universe splits. In one branch, we see a dead cat. In another branch, we see a live cat. Both outcomes are real. Both branches exist. From inside each branch, it appears that the wave function collapsed, that one outcome was randomly selected. But from a God's eye view outside the multiverse, there's no collapse. There's just continuous deterministic evolution of the universal wave function, branching into multiple parallel realities. The cat is alive in one universe, dead in another. Both versions of the cat are equally real. Both versions of you, the you who sees a dead cat and the you who sees a live cat, are equally real. They exist in different branches of reality, unaware of each other, each convinced that their outcome is the outcome. This interpretation avoids the measurement problem. There's no collapse, no special role for consciousness, no boundary between quantum and classical, just endless branching of reality into parallel worlds. But it comes at a cost. An infinity of parallel universes, proliferating with every quantum event, forever inaccessible to each other. It's elegant mathematically, but ontologically extravagant. Is it really more reasonable to believe in infinite parallel worlds than to accept that wave functions collapse? The objective collapse theories propose that wave functions do collapse, but not because of consciousness or measurement. Instead, they collapse spontaneously, randomly, according to processes we don't yet fully understand. Perhaps gravity plays a role. Perhaps there are hidden mechanisms that cause decoherence at certain scales. In these theories, the cat wouldn't remain in superposition for long. The collapse would happen quickly, perhaps within microseconds, because the cat is a large, complex, warm system interacting constantly with its environment. The superposition would decay into a definite state, alive or dead, long before we open the box. This feels more reasonable. It preserves quantum mechanics for microscopic systems while explaining why we don't see macroscopic superpositions, but these theories modify the Schrödinger equation, adding new collapse terms, and we don't yet have experimental evidence for these modifications. Standard quantum mechanics works perfectly well. Why add complications? There's another piece of the puzzle, decoherence. This isn't a full interpretation of quantum mechanics, but it's a mechanism that explains why we don't observe macroscopic superpositions in practice, even if they exist in principle. Decoherence is what happens when a quantum system interacts with its environment. The system becomes entangled with countless environmental degrees of freedom: air molecules, photons, thermal vibrations, electromagnetic fields. The system's quantum coherence, its ability to exhibit interference and superposition, rapidly decays. The cat in the box is warm. It's radiating heat. Infrared photons are bouncing off its fur. Its atoms are vibrating, colliding with air molecules. Every one of these interactions entangles the cat's quantum state with the environment's quantum state. Within an incredibly short time, nanoseconds, microseconds at most, the cat's state becomes hopelessly entangled with its environment. The superposition of alive and dead decoheres into a classical mixture of alive or dead. From an external perspective, it looks like the wave function has collapsed. The interference terms that would allow us to observe quantum behavior vanish. The cat becomes, for all practical purposes, classical. But decoherence doesn't solve the measurement problem. It doesn't tell us whether the wave function actually collapses or just appears to collapse. It doesn't tell us which outcome becomes real. It just explains why superpositions are invisible at macroscopic scales. The cat might still be in superposition, technically, but the superposition has decohered so thoroughly that it's empirically indistinguishable from a collapsed state. We can't perform interference experiments on cats. We can't observe their quantum coherence. Decoherence destroys it too quickly. So perhaps Schrödinger's cat isn't as paradoxical as it seems. Perhaps the cat never actually exists in observable superposition, because decoherence happens too fast. Perhaps the thought experiment is unrealistic because it imagines perfect isolation that can't be achieved in practice. but the conceptual problem remains. In principle, according to the Schrödinger equation, the cat is in superposition. Decoherence only hides it. It doesn't eliminate it. And if we could somehow perfectly isolate the cat, eliminate all environmental interactions, cool it to absolute zero, then, in principle, the superposition would persist. The cat would genuinely be alive and dead. We'll never perform this experiment. It's impossible in practice. But the theoretical possibility is what troubles us. Quantum mechanics, taken seriously, predicts that macroscopic objects can exist in superposition. And we don't know where or why that stops being true. Let's consider a different angle, a more disturbing angle. Suppose the cat is conscious. Suppose the cat has subjective experience. Qualia, what philosophers call phenomenal consciousness. The raw feeling of being alive, of experiencing. When the cat is in superposition, what does the cat experience? Does the cat experience both being alive and being dead simultaneously? What would that even mean? Or does the cat's consciousness collapse the wave function? Does the cat's observation of its own state, its awareness of being alive or dead, force the superposition to resolve? If so, then consciousness becomes a physical phenomenon, something that causes wave function collapse, something with a unique role in the laws of physics. Some physicists have proposed exactly this. Eugene Wigner, a Nobel laureate, argued that consciousness is necessary for wave function collapse. John von Neumann, one of the greatest mathematicians of the 20th century, suggested that the chain of quantum entanglement continues until it reaches a conscious observer, and only then does collapse occur. In this view, the Geiger counter, the hammer, the vial, the cat's body, all remain in superposition. But when the information reaches the cat's consciousness, or when we, as conscious observers, open the box, the wave function collapses. Consciousness creates reality. This is called the consciousness causes collapse interpretation, and it's deeply controversial. It implies that consciousness is not an emergent property of complex physical systems, but something fundamental, something woven into the fabric of physics at the deepest level. It raises more questions than it answers. What counts as consciousness? Does a cat have enough consciousness to collapse wave functions? What about a mouse? An insect? A bacterium? Where is the threshold? And what was the universe before consciousness evolved? Was everything in superposition for 10 billion years, waiting for the first conscious being to observe it and make it real? Most physicists reject this interpretation, not because it's been experimentally disproven, we don't know how to test it, but because it seems unnecessary, anthropocentric, and philosophically troubling. But we can't completely rule it out. We don't understand consciousness. We don't understand why subjective experience exists, or how it emerges from physical systems, or what role, if any, it plays in fundamental physics. Perhaps consciousness is fundamental. Perhaps it does collapse wave functions. Perhaps the universe needed observers to become real. We don't know, and the fact that we don't know, after a century of quantum mechanics, is humbling. Let's bring this closer to home, to your body. You are made of quantum particles. Every atom in your body obeys quantum mechanics. Electrons in your neurons exist in superposition until measured. Photons in your retina are in superposition until they're absorbed. Molecules in your DNA occupy quantum states. Quantum effects are not just theoretical curiosities. They're essential to life. Photosynthesis, the process by which plants convert light into chemical energy, relies on quantum coherence. Photons absorbed by chlorophyll molecules exist in superposition, simultaneously exploring multiple pathways, finding the most efficient route to transfer energy. Enzymes, the molecular machines that catalyze chemical reactions in your body, may use quantum tunneling. Particles tunnel through energy barriers that would be insurmountable classically, allowing reactions to proceed faster than classical chemistry would predict. Your sense of smell might be quantum. Some theories suggest that olfactory receptors distinguish molecules not by their shape, but by their vibrational frequencies, using quantum tunneling to detect minute differences that classical mechanisms couldn't sense. Even your consciousness, the mysterious phenomenon of subjective experience, might have quantum aspects. Some researchers, like Roger Penrose and Stuart Hameroff, have proposed that quantum processes in brain microtubules play a role in consciousness. This is highly speculative and not widely accepted, but it's an active area of research. The point is, you are not separate from the quantum realm. You are made of it. Quantum superpositions are happening in your body right now, constantly. Electrons in your neural synapses, photons in your eyes, molecules in your cells. These superpositions decohere rapidly. Your body is warm, wet, noisy, the opposite of the isolated cold conditions needed to maintain quantum coherence. But before decoherence, before collapse, the superpositions are real. Particles in your body genuinely exist in multiple states simultaneously, however briefly. You are, in a sense, a perpetual Schrödinger's cat. A system balanced between quantum and classical, constantly collapsing superpositions into definite states, constantly creating reality from possibility, moment by moment, breath by breath. Schrödinger's cat is not just about cats. It's about the nature of reality, about what it means for something to be real, about the role of observation, measurement, consciousness in determining what exists. If quantum mechanics is correct, and every experiment says it is, then reality at the fundamental level is not definite until observed. Objects don't have properties independent of measurement. The universe doesn't contain hidden facts waiting to be discovered. Instead, it contains possibilities, potentials, superpositions, and these only become definite through the act of observation. This is profoundly strange. It contradicts our deepest intuitions about the world. We believe in an objective reality that exists independent of us. We believe that if a tree falls in the forest with no one around, it definitely either makes a sound or doesn't make a sound. We believe that the moon is there even when we're not looking at it. Einstein believed this. He said, "I like to think the moon is there even if I am not looking at it." He refused to accept that observation creates reality. He spent decades trying to prove quantum mechanics incomplete, trying to restore objective realism, trying to show that particles have definite properties even when unmeasured. He failed. Bell's theorem, proved in 1964 and experimentally confirmed many times since, shows that no theory with local hidden variables can reproduce quantum mechanics predictions. If quantum mechanics is right, and it is, then either locality or realism must be abandoned. Either, 1, particles can instantly affect each other across arbitrary distances, non-locality, or 2, particles don't have definite properties until measured, non-realism. Both options are disturbing. Both violate common sense. But these are our only choices, and experimental evidence strongly suggests that both are true. Reality is both non-local and non-real. The universe is not what we thought it was. Let's pause here. Let's breathe. You've descended deep into the quantum rabbit hole. You've confronted one of the most disturbing thought experiments in physics. You've seen that reality, at its foundation, is indefinite, probabilistic, dependent on observation in ways that challenge everything we believe about existence. The cat in the box is alive and dead simultaneously, until observed. This is what quantum mechanics predicts. This is what the math says. And we have no compelling reason to think it's wrong. Whether you accept this literally, whether you believe in actual macroscopic superpositions, or in many worlds, or in consciousness-driven collapse, or in objective collapse mechanisms, depends on your interpretation. And interpretations are, fundamentally, philosophical choices. The math is the same. The predictions are the same, only the story we tell ourselves about what's really happening changes. But the observations are undeniable. The quantum realm behaves this way. Particles exist in superposition. Measurement changes outcomes. Observation creates reality. These are facts, confirmed by countless experiments. So perhaps the question isn't whether the cat is alive or dead. Perhaps the question is what we mean by alive, by dead, by is. Perhaps our language, evolved in a classical world, simply isn't equipped to describe quantum reality accurately. Perhaps we need new concepts, to certain nausea, new words, new ways of thinking that transcend the either-or logic of classical physics and embrace the both and neither logic of quantum mechanics. Or perhaps we need to accept mystery, to acknowledge that reality at its deepest level might be incomprehensible to minds like ours, minds that evolved to hunt and gather on the African savanna, not to understand the quantum substrate of existence. As sleep approaches, as consciousness begins to dissolve, consider this. You spend a third of your life in a state that's neither fully conscious nor fully unconscious. Sleep is a superposition of states, REM and non-REM, dreaming and not dreaming. aware and unaware. You cycle through these states, existing in ambiguous in-between places that are hard to define, hard to measure, hard to know. Perhaps sleep is the closest we come to experiencing quantum superposition directly. Perhaps in dreams, where logic dissolves and contradictions coexist, where you can be yourself and someone else simultaneously, where time flows backward and forward without constraint. Perhaps there, in the dream state, you glimpse what quantum reality is actually like. The cat sleeps in its superposition, alive, dead, both neither, waiting for observation to collapse the wave function to choose a definite state, to make reality real. And you sleep too. Consciousness fading, awareness diffusing, the boundaries of self becoming fuzzy, probabilistic, indefinite. Rest now in the quantum ambiguity. Rest in the superposition. Rest in the mystery that Schrödinger revealed and could never solve. The cat waits. The box remains sealed, and reality hangs in the balance, undecided, until the moment of observation creates what we call truth. Sleep well, dream deeply, and know that somewhere, in some sense, you too are Schrödinger's cat, alive and dead, here and not here, being and not being, waiting for observation to make you real. Einstein called it spooky action at a distance. He meant it as an insult, as proof that quantum mechanics couldn't be right, as evidence that the theory was incomplete, that something was missing, that deeper laws waited to be discovered. He was wrong. The spookiness is real. The action at a distance is real, and it's far stranger than Einstein ever imagined. We're going to talk about quantum entanglement, a phenomenon so bizarre, so counterintuitive, so fundamentally incompatible with our notions of space and causality that even now, after decades of experimental confirmation, it still feels impossible. When their properties become linked so intimately that measuring one particle instantly affects the other, regardless of the distance between them, not in a few seconds, not at light speed, instantly. Faster than light, faster than anything. Two particles can be entangled, separated by any distance, meters, kilometers, light years, and when you measure one, the other responds. Immediately. As if distance doesn't matter. As if space itself is an illusion. As if the particles are still connected by something deeper than any physical medium, something that ignores the geometry of space-time entirely. This isn't science fiction. This isn't speculation. This is observed reality. This is what happens. This is what the universe does, and no one truly understands why. In 1935, the same year Schrödinger proposed his famous cat, Einstein published a paper with two colleagues, Boris Podolsky and Nathan Rosen. It's known as the EPR paper, after their initials, and it was meant to prove that quantum mechanics was incomplete. Here's the thought experiment they proposed. Imagine a particle that decays into two smaller particles. These particles fly apart in opposite directions. By conservation of momentum, if one particle is moving left, the other must be moving right. If one has spin up, the other has spin down. Their properties are correlated, perfectly, mathematically correlated, because they came from the same source. Now, according to quantum mechanics, before you measure them, neither particle has a definite spin. Each exists in superposition, simultaneously spin up and spin down. Only when you measure one particle does its spin become definite. The wave function collapses. The superposition resolves into a specific state. But here's the strange part. The instant you measure one particle and find it has spin up, the other particle, which might be kilometers away by now, instantly becomes spin down. Not because any signal travels between them, not because they communicate, but because they share a single quantum state. They're entangled. Measuring one collapses the shared wave function and determines both outcomes simultaneously. Einstein said this was absurd. He argued that the particles must have definite spins from the moment they're created. Quantum mechanics just doesn't tell us what those spins are. There must be hidden variables, additional information beyond the wave function, that determines each particle's properties. The particles aren't really in superposition. They have definite states all along. We're just ignorant of what those states are. This would restore common sense. It would mean particles have properties independent of measurement. It would mean reality is objective, local, deterministic. It would mean the universe makes sense. But Einstein was wrong. For nearly 30 years, Einstein's hidden variable theory seemed plausible. It seemed like the reasonable explanation. Many physicists assumed that eventually deeper theories would be discovered that would restore determinism and eliminate the weirdness of quantum mechanics. Then, In 1964, a physicist named John Bell proved a theorem that changed everything. Bell showed mathematically that any theory with local hidden variables, any theory where particles have definite properties and where no influence travels faster than light, must satisfy certain inequalities, certain statistical constraints on the correlations between measurements. Quantum mechanics predicts correlations that violate these inequalities. So either quantum mechanics is wrong or local hidden variable theories are wrong. The choice seemed clear. Surely Einstein was right. Surely hidden variables exist. Surely quantum mechanics would turn out to be an approximation, and Bell's inequalities would be satisfied when proper experiments were performed. But they weren't. Starting in the 1970s and continuing to the present day, experiment after experiment has confirmed that Bell's inequalities are violated. The correlations predicted by quantum mechanics are observed. The correlations allowed by local hidden variables are exceeded. Entanglement is real. The instant correlations are real. The non-locality is real. Particles genuinely don't have definite properties before measurement. The universe genuinely doesn't contain hidden information that determines outcomes in advance. And measuring one particle genuinely affects its entangled partner instantaneously, regardless of distance. Einstein's spooky action at a distance is how reality actually works. Let's make this concrete. Let's imagine you're part of an entanglement experiment. We create two photons in a special quantum state, a maximally entangled state where the photons' polarizations are perfectly correlated but individually undefined. We send one photon to you, we send the other to a colleague halfway around the world. Before measurement, neither photon has a definite polarization. Each exists in a superposition of horizontally polarized and vertically polarized. The quantum state looks like this. Vertical bar state equals 12061 versus 51 versus 81 H2. The subscripts indicate the two photons. The state says the first photon is horizontal and the second is vertical. Oregon, the first is vertical and the second is horizontal. Superposition. Both possibilities simultaneously present. Now you measure your photon's polarization. You orient your detector vertically. The photon either passes through vertical polarization or doesn't, horizontal polarization. Let's say it passes through. Your photon is vertically polarized. At that instant, that exact instant, your colleague's photon halfway around the world becomes horizontally polarized, not because any signal traveled from your detector to theirs, not because the photons communicated, but because you and your colleague are measuring aspects of a single shared quantum state. Your measurement collapsed the wave function for both photons simultaneously. If you measure again, rotating your detector to a different angle, your colleague's results change correspondingly. The correlations persist. Every measurement you make is reflected instantly in the statistics of their measurements, and vice versa. You might think, maybe information is traveling between the photons faster than light. Some hidden signal, some quantum carrier wave that we haven't detected yet. But no, Bell's theorem rules this out. The correlations are too strong, too perfect. They exceed what any theory with local interactions, including faster-than-light signals, could produce. The only way to explain the observations is to accept non-locality, to accept that entangled particles are, in some deep sense, not separate entities but parts of a single quantum system that transcends space. Asterisk, the quantum telephone that doesn't work. You might be thinking, this is amazing. We can use entanglement to communicate faster than light. I measure my particle, and instantly, the result affects your particle thousands of miles away. We've beaten the cosmic speed limit. But no, it doesn't work. And this is one of the deepest and most frustrating aspects of quantum mechanics. You cannot use entanglement to send information faster than light. You cannot use it to communicate. Despite the instant correlations, despite the non-local connections, despite the fact that measuring one particle affects the other instantaneously, you can't exploit this to send messages. Why not? Because the results you observe are random. When you measure your photon, you get a random outcome. It's a 50-50 chance of vertical or horizontal. You can't control the result. You can't encode information in it. Your colleague, measuring their photon, also gets random results. 50-50 chance. They see nothing but random noise. The correlations only become visible when you and your colleague compare notes, when you bring your lists of measurements together and look at them side by side. Then you see the pattern. Then you see that your results were perfectly anti-correlated. When yours was vertical, theirs was horizontal. When yours was horizontal, theirs was vertical. Every single time. But this comparison requires classical communication. Sending the lists via email or phone or physical mail, and that communication is limited by the speed of light. The correlations exist instantly, but discovering them requires slow classical information exchange. So entanglement doesn't violate relativity's prohibition on faster-than-light signaling. It exists in a strange loophole where effects can be instantaneous, but information transfer cannot. This has troubled physicists for decades. How can there be instant correlations without instant communication? How can cause and effect be separated? How can the universe allow non-local connections while preserving causality? The answer, if there is one, seems to be that quantum mechanics is deeply contextual. The results you observe depend not just on the state of your particle, but on what measurement you choose to perform, and on what measurements are performed elsewhere on entangled partners. Information is non-local, but it's only information in a quantum sense. Probability amplitudes, wave function components, abstract mathematical objects that have no classical analog. When you try to extract classical information, bits, messages, data, you can't do it faster than light. The quantum information is non-local, but classical information respects locality. It's as if the universe has two layers. A quantum layer where everything is connected, where distance is illusory, where entanglement links particles across space, and a classical layer where causality holds, where light speed is the limit, where information flows normally. But we're made of the quantum layer, and the two are forever entangled in ways we're only beginning to understand. The experiments we've described so far involve entangled particles separated in space, but entanglement transcends time as well. Imagine we create an entangled pair of photons. We measure one immediately. We store the other, perhaps in a quantum memory, a system that can preserve quantum states for extended periods. We wait. Hours, days, years. Then we measure the stored photon, and we find that it's still entangled with the measurement we made long ago. The correlation persists across time. The past measurement and the future measurement are connected by quantum entanglement, as if time itself is less fundamental than the quantum state. Some experiments have demonstrated even stranger temporal effects. Delayed choice experiments show that decisions made in the present can affect which past events become real. Quantum erasers demonstrate that erasing information about the past can change what we observe about the events that have already occurred. The past is not fixed, the future is not determined. And the boundary between them is blurry, negotiable, dependent on what measurements are made and when. Entanglement doesn't just connect particles across space, it connects moments across time. It weaves past and future into a single quantum tapestry where cause and effect, before and after, lose their absolute meanings. Let's go deeper. Let's ask a disturbing question. If entangled particles are instantly correlated regardless of distance, are they really separate? Our intuition says yes. One particle is here, the other is there. They occupy different locations. They're separate entities. But quantum mechanics says something else. It says that entangled particles don't have independent wave functions. They share a single wave function, a single quantum state. That describes them together. You can't write down a state for one particle and a separate state for the other. They're not separate systems, they're one system. The state vector for two entangled particles exists in a combined Hilbert space, the tensor product of the individual spaces, and in this combined space the particles are not factorizable. Their state cannot be written as a product of individual states. They're correlated in ways that transcend any classical connection. In a very real sense, entangled particles are not two things. They're one thing extended across space, one system with parts that appear separate but are fundamentally unified. This raises a profound question. What do we mean by separate? What does it mean for two objects to be distinct? In classical physics, separateness is simple. Two objects occupy different regions of space. They have separate properties. They can be described independently. What happens to one doesn't affect the other unless there's a physical interaction between them. In quantum mechanics, none of this is necessarily true. Objects can be entangled. Their properties can be correlated without any ongoing interaction. What happens to one can instantly affect the other. and their descriptions are not independent. They're aspects of a single quantum state. Maybe separateness is an illusion. Maybe the universe is fundamentally holistic. Maybe what we perceive as distinct objects are really patterns in a unified quantum field, temporarily manifesting as separate entities, but always secretly connected, always entangled, always one. Here's where it gets truly cosmic. Truly mind-bending. Everything in the universe was once close together. At the Big Bang, all matter and energy occupied an infinitesimally small region. Everything was in contact. Everything interacted. Everything became entangled. As the universe expanded, particles separated, galaxies formed, stars ignited, planets coalesced. Life emerged, consciousness arose. Billions of years passed. Matter spread across billions of light years. But the entanglement persists. It never goes away. Particles that interacted 13.8 billion years ago, near the beginning of the universe, are still entangled now. Their quantum states are still correlated. They're still, in some sense, connected. Every particle in your body was once entangled with particles now in distant galaxies. Every atom you're made of has quantum correlations with atoms light years away, atoms you'll never encounter, atoms that exist in regions of space you'll never observe. The universe is not a collection of separate objects. It's a single, vast, impossibly complex quantum state. Everything is entangled with everything else. Not strongly, most entanglements are weak, diluted by countless interactions and measurements over eons. But the correlations are there, woven into the fabric of reality, connecting you to the most distant quasar, to the earliest moments of cosmic history, to regions of space beyond the observable universe. You are not separate from the cosmos. You're part of it, not metaphorically, not poetically, literally. Your quantum state is entangled with the quantum state of everything that exists, everything that has ever existed, everything that will ever exist. Quantum mechanics reveals something that mystics and philosophers have long intuited. The universe is one. Separation is illusion. Distance is appearance. At the deepest level, all is connected. All is one. Despite its philosophical implications, entanglement is not just abstract theory. It's useful. It's technology. We're learning to harness it. Quantum cryptography uses entanglement to create unbreakable codes. Two parties share entangled particles. They use measurements of these particles to generate encryption keys. Any attempt to eavesdrop on the communication disturbs the entanglement, revealing the eavesdropper's presence. The laws of physics themselves guarantee security. Quantum computing uses entanglement to perform calculations that classical computers cannot. Quantum bits, qubits, can exist in superposition and can be entangled with each other. A quantum computer with just a few hundred qubits can exist in more states simultaneously than there are atoms in the universe. Problems that would take classical computers longer than the age of the universe can potentially be solved in minutes. Quantum teleportation uses entanglement to transmit quantum states across space. Not matter, not energy, but information. Pure quantum information. The state of one particle can be transferred to another particle far away, using entanglement and classical communication. The original particle's state is destroyed in the process. You can't clone quantum information, but the distant particle becomes an exact copy. These technologies are in their infancy, but they're real. They work. Companies and governments are investing billions in quantum technologies. The first quantum computers already exist, though they're primitive. Quantum communication networks are being built. The quantum revolution is underway, and it's all based on entanglement, on the spooky action Einstein hated, on the non-local correlations that shouldn't exist but do, on the quantum connections that link particles across space and time. We understand how entanglement works mathematically. We can calculate, we can predict, we can build technologies based on it. But do we understand what it means? When two particles are entangled, and we measure one and the other instantly responds, what's actually happening? Is information traveling faster than light? Are the particles connected by some hidden medium? Are they reaching through higher dimensions? Are they the same particle, somehow existing in two places? We don't know. We can describe what happens. We can't explain why it happens. We can't visualize it. We can't create an intuitive picture that makes sense. Some physicists argue we shouldn't try. Quantum mechanics is the picture. The wave function is reality. There's nothing deeper to understand. The math is the explanation. Others argue there must be something more, some underlying reality that quantum mechanics describes but doesn't reveal, some deeper structure that would make entanglement comprehensible, that would restore intuition, that would show us how the universe really works. Both views might be right, or both might be wrong. After a century of quantum mechanics, we still argue about its interpretation. We still don't agree on what the theory is telling us about reality. But the observations are undeniable. The experiments are conclusive. Entanglement is real. Non-locality is real. The universe is connected in ways that transcend space and time. Einstein was wrong to reject it. But perhaps he was right to be disturbed by it. Perhaps spooky action at a distance is an appropriate name for something that violates our deepest intuitions, that challenges our understanding of causality and locality, that suggests the universe is far stranger than we ever imagined. As you lie here drifting towards sleep, consider this: you are entangled with everything. Not strongly, not in ways you can directly perceive. Your quantum coherence with distant objects is weak, overwhelmed by local decoherence, lost in the noise of thermal fluctuations and environmental interactions. But the connections are there, woven into your quantum state, linking you to the room around you, to the air you breathe, to the planet beneath you, to the sun above, to the stars in the sky, to galaxies billions of light years away. Every particle in your body has interacted with countless other particles. Those interactions created entanglements. Those entanglements persist, however weakly, forever. You are not an isolated island of consciousness floating in an empty void. You are a node in a cosmic web of quantum correlations. You are connected intimately and indelibly to everything that exists. This connection is not mystical. It's physical. It's mathematical. It's quantum mechanical. It's verified by experiment and harnessed by technology. And yet it feels mystical. It feels profound. It feels like physics is telling us what spiritual traditions have always taught, that separation is illusion, that all is one, that consciousness and cosmos are fundamentally unified. Perhaps they're both right. Perhaps quantum mechanics is the bridge between science and spirituality. Perhaps entanglement is the physical manifestation of a deeper unity that encompasses not just matter and energy, but consciousness and meaning and existence itself. Or perhaps we're projecting meaning onto mathematics. Perhaps the universe is just quantum fields and probability amplitudes and wave function collapse, with no deeper significance, no hidden purpose, no cosmic consciousness. We don't know. We can't know. These are questions beyond physics, beyond experiment, beyond what science can definitively answer. But we can observe. We can measure. We can verify that entanglement exists, that particles are connected, that the universe is unified in ways that transcend space and time. And we can rest in that knowledge, rest in the certainty that you are not alone, not separate, not isolated. You are connected quantum mechanically, physically, undeniably, to everything that exists. Sleep now, dream now, and know that as you drift into unconsciousness, as your brain states shift and your awareness fades, the quantum entanglements that link you to the cosmos persist. The connections remain. The unity endures. You are one with the universe, not metaphorically, literally, through quantum entanglement, through the spooky action that Einstein rejected but reality embraces. The cosmos is connected. You are part of that connection. And tomorrow, when you wake, when consciousness returns, when the boundaries of self reassert themselves, remember that beneath the appearance of separation, the quantum reality of unity remains, forever entangled, forever connected, forever one. We've descended far into the quantum realm. We've seen that particles are waves and waves are particles. We've learned that nothing has definite properties until observed. We've witnessed cats that are alive and dead simultaneously. We've discovered connections that transcend space and time. Now, as sleep approaches, as consciousness begins to dissolve at the edges, we're going to take one final step. We're going to ask the biggest question of all. Not what is the quantum realm, not how does it work, but why? Why does the universe behave this way? What does it mean? And what does quantum mechanics tell us about the deepest nature of reality itself? This is where physics becomes philosophy, where mathematics becomes metaphysics, where the boundaries between science and spirituality, between knowledge and mystery, between what we can know and what we can only wonder about. These boundaries dissolve just as surely as your waking consciousness is dissolving now into the dream state. Let's ask the questions that have no answers. Let's contemplate the mysteries that remain even after a century of quantum mechanics. Let's peer into the deepest levels of reality and see what looks back. We've been taught that empty space is empty, that a vacuum is nothing, absence, void, the complete lack of anything. But quantum mechanics says otherwise. The vacuum empty space is not empty at all. It seethes with activity. It fluctuates. It creates and destroys. It contains infinite energy, infinite possibilities, infinite potential. This is because of the Heisenberg uncertainty principle. Remember, energy and time are conjugate variables, like position and momentum. The more precisely one is defined, the less precisely the other can be. And this has a strange consequence. For brief moments, the universe can violate energy conservation, as long as the violation is paid back quickly enough. Delta E times delta T greater than 2 delta E times delta T must be greater than or equal to Planck's constant divided by 2. The more energy you borrow, the faster you must return it. But you can borrow. The universe allows it. The vacuum allows it. So at every point in space, at every moment in time, particle-antiparticle pairs are spontaneously appearing from nothing. An electron and a positron flash into existence, exist for a tiny fraction of a second, perhaps 10 by 20 seconds, then annihilate each other and disappear back into the vacuum. These are called virtual particles. They're not real in the sense that we can directly observe them or that they persist, but they're not imaginary either. They have measurable effects. The Casimir effect, for example. Place two metal plates very close together in a vacuum. Fewer virtual particles can exist between the plates than outside them, because only certain wavelengths fit in the narrow gap. This creates a pressure difference. The plates are pushed together by the quantum vacuum itself. This force has been measured. It's real. It's caused by virtual particles that exist and don't exist, that are real and not real, that emerge from nothing and return to nothing. The vacuum is alive. It's a quantum foam, a seething ocean of possibility, where particles are constantly being created and destroyed, where energy fluctuates wildly at the smallest scales, where even empty space is full. And this raises a disturbing question. What is nothing? If empty space contains infinite virtual particles, infinite quantum fluctuations, infinite potential energy, is it really empty? Is there such a thing as true nothingness? Or is the vacuum the most fundamental state of reality? Not absence, but presence. Not nothing, but everything in potential form. Perhaps the vacuum is what reality is. Perhaps matter, energy, particles, fields, all of it, is just excitations of the vacuum, ripples on the surface of an infinite quantum ocean, temporary patterns that emerge from nothing and return to nothing, while the nothing itself endures, eternal and infinite. You are a pattern in the vacuum, a configuration of quantum fields that has achieved sufficient complexity to become conscious, to observe itself, to wonder about its own existence, and when you die, you return to the vacuum, not to nothingness, but to the infinite potential from which you came. The atoms of your body scatter, the energy dissipates, the pattern dissolves, but nothing is lost. Everything returns to the quantum foam, ready to be reconfigured, to emerge again in new forms, in new patterns, in new moments of temporary existence. There's an interpretation of quantum mechanics that we've touched on but haven't fully explored. It's called the many worlds interpretation, and it's both the most elegant and the most extravagant solution to the measurement problem. Hugh Everett proposed it in 1957. The idea is simple. The wave function never collapses, ever. Superpositions are real and persist. When a measurement happens, when a quantum system interacts with its environment, the universe doesn't choose one outcome. All outcomes occur, but they occur in different branches, different worlds, different parallel realities that split off from each other, never to interact again. When you perform a quantum measurement, say, observing the spin of an electron, the universe splits. In one branch, you observe spin up. In another branch, you observe spin down. Both versions of you are real. Both versions of the universe are real. They've just become separate, isolated from each other, occupying different branches of the universal wave function. Schrödinger's cat doesn't collapse into alive or dead. both outcomes occur. The universe splits into two branches. In one, the cat is alive and you observe a living cat. In the other, the cat is dead and you observe a dead cat. Both cats are real. Both versions of you are real. This happens constantly. With every quantum interaction, every particle collision, every photon absorption, every moment of observation, the universe is splitting, branching, proliferating into countless parallel realities, each one as real as any other. Right now, as you read this, the universe is splitting trillions upon trillions of times per second. Every quantum event in your body, in the air around you, in the device you're reading from, in the distant stars, each one creates new branches, new worlds, new versions of reality. There are versions of you where you made different choices, turned left instead of right, said yes instead of no, pursued different careers, different relationships, different lives. All of these versions are real, existing in parallel branches of the universal wave function. There are versions of Earth where history unfolded differently, where different empires rose and fell, where different technologies were developed, where humanity evolved slightly differently, or not at all. There are versions of the universe where the fundamental constants of physics are different, where gravity is stronger or weaker, where electrons have different masses, where stars never formed or formed differently, creating utterly alien cosmic architectures. All of this is real. All of this exists, not as speculation, not as fantasy, but as necessary consequences of quantum mechanics if, and this is the key if, the wave function never collapses, if superposition is truly fundamental and irreducible. The many worlds interpretation solves the measurement problem elegantly. There's no collapse, no special role for consciousness, no boundary between quantum and classical, just continuous deterministic evolution of the wave function branching into infinite parallel realities. But it comes at an ontological cost, an infinity of worlds, an infinity of versions of you, an infinity of histories, all equally real, all inaccessible to each other. Is this truth, or is it mathematics taken too literally? We don't know. We may never know. The other branches, by definition, can't be observed from our branch. The theory is empirically identical to standard quantum mechanics in terms of predictions, but wildly different in terms of what it says about reality. And yet, many physicists find it compelling. It's the simplest interpretation in some ways. It requires no additional postulates, no collapse mechanism, no special rules, just the Schrödinger equation, applied consistently to everything. Perhaps you exist in infinite variations. Perhaps every choice you make creates branches where you made different choices. Perhaps the you reading this right now is just one of countless versions, each as real as any other, each living out different possibilities in parallel worlds that will never meet. Perhaps death is not an ending but a branching. In some branches you die, in others you live, and the consciousness that is you, whatever that is, continues in the branches where survival occurs, experiencing an immortality of sorts, forever finding itself in worlds where it didn't die, because the worlds where it died are no longer accessible to its experience. This is quantum immortality, a strange consequence of many worlds thinking. It's speculative, unverifiable, possibly nonsense, but it's also a logical consequence of taking the interpretation seriously. The multiverse is vast beyond comprehension, and you are a thread woven through it, existing in countless variations, living countless lives, making countless choices, all of them real, all of them you. Throughout this journey, we've encountered a troubling theme. Observation matters. Measurement changes outcomes. Consciousness, or at least interaction, or information gain, or something we call measurement, plays a fundamental role in quantum mechanics. But what is an observer? What counts as a measurement? Where is the boundary? Does a particle detector count as an observer? Does a cat? Does a bacterium? Does a thermostat? Does a rock? If consciousness is required, then what level of consciousness? Human? Animal? Any living thing? Any information processing system? These questions have no agreed upon answers, and they're important. Because if observation creates reality, then understanding what counts as observation is essential to understanding what reality is. Some physicists argue that consciousness is fundamental, that minds collapse wave functions, that the universe needed observers to become real, and that before consciousness evolved, reality was in superposition, potential but not actual. This is a radical view. It makes consciousness not an emergent property of complex physical systems, but something fundamental, something woven into physics at the deepest level. Others argue that consciousness is irrelevant, that any physical interaction counts as a measurement, that decoherence, the interaction between a quantum system and its environment, is sufficient to create the appearance of wave function collapse, without any special role for minds or awareness. This is the more common view among physicists. It's less anthropocentric. It doesn't require consciousness to be fundamental. It explains why macroscopic objects behave classically without invoking anything mysterious, but it doesn't fully solve the measurement problem. Decoherence explains why we don't observe superpositions. It doesn't explain how or why superpositions become definite outcomes. It doesn't tell us which outcome becomes real or whether all outcomes become real in different branches. Perhaps the question is ill-posed. Perhaps observer isn't a fundamental category. Perhaps measurement is just a special kind of interaction, and the mystery dissolves when we understand interactions better. Or perhaps consciousness really is fundamental. Perhaps the universe is not just physical but also mental, and quantum mechanics is the bridge between them, the place where mind and matter meet, where observation literally creates reality. We don't know. And this not knowing is not a temporary gap in our understanding. It's a fundamental uncertainty that may be woven into the nature of existence itself. John Wheeler, the physicist who proposed the delayed choice experiment, had a vision of what he called the participatory universe. The idea is that the universe doesn't just exist independent of observers. Instead, observers participate in creating reality. The act of observation is not passive, it's creative, generative, constitutive. Wheeler drew a diagram, a large letter U representing the universe, with an eye at the bottom of the U looking back at the beginning. The universe creates observers. Observers observe the universe, and through observation, they participate in determining what the universe is and was. The past is not fixed until observed, the future is not determined until realized. And observers, conscious, measuring, information-gathering observers, are the agents that collapse possibility into actuality, that make the potential real, that create history through the act of witnessing it. This is a strange loop, a self-referential system. The universe creates consciousness. Consciousness observes the universe. Observation affects the universe. The universe evolves. Consciousness evolves. And the cycle continues, with each element shaping the other, neither fully independent, neither fully primary. Perhaps this is the deepest truth of quantum mechanics. Not that observation creates reality in a simple causal sense, but that observation and reality are co-creative, interdependent, each one incomplete without the other. There is no objective reality independent of observation. There is no observation independent of reality. There is only the participatory dance between them, the quantum entanglement between observer and observed, between mind and world, between consciousness and cosmos. You are not separate from the universe. You are not a passive witness to reality. You are a participant, an active creator. Through your observations, through your measurements, through your conscious experiencing of the world, you are helping to create what the world is. Every moment you observe is a moment you collapse wave functions, resolve superpositions, create definite reality from quantum potential. You are, in a very literal sense, bringing the world into being with every glance, every thought, every measurement. This is not solipsism. It's not saying you create reality by yourself, or that reality is just your imagination. It's saying that reality is a collaborative creation. The universe provides the quantum potential. Observation, yours, mine, every observer's, collapses that potential into actuality. And the actuality we experience is the sum of all observations, all measurements, all participatory acts of reality creation. We've traveled far, from particles that are waves, to superpositions that are real, to cats that are alive and dead, to entanglements that transcend space, to observers that create reality, to a universe that may be infinite in its possibilities, branching into countless worlds, each one as real as any other. And yet, despite all this knowledge, despite a century of quantum mechanics, despite thousands of experiments and millions of calculations, we still don't understand. We don't know what the wave function is. Is it real? Is it just information? Is it a physical field? Is it just a mathematical tool? We don't know what happens during measurement. Does the wave function collapse? If so, how? Why? Or does the universe split? Or is there no collapse at all, just decoherence that makes it appear as if collapse occurred? We don't know what counts as an observer. Consciousness? Any interaction? Information gain. Where is the boundary between quantum and classical? We don't know why the universe is quantum. Why superposition? Why probability? Why uncertainty? Why this strange, counterintuitive set of rules instead of the classical, deterministic laws that seem so much more sensible? These are not gaps in our knowledge that will be filled by more experiments or better theories. These are mysteries that touch the foundation of existence itself. Questions about the nature of reality, the role of consciousness, the meaning of existence. Quantum mechanics works. It predicts. It explains. It enables technologies that wouldn't exist otherwise. But it doesn't tell us what reality is, only what we'll observe when we look, and perhaps that's the deepest lesson. Perhaps reality isn't something that exists independent of observation. Perhaps asking, what is reality really like when we're not looking, is like asking, what does silence sound like? Or, what color is invisible? Perhaps the question is meaningless. Perhaps reality is observation, and observation is reality, and the two can't be separated. As sleep claims you, as consciousness dissolves into dreams, as the boundaries between self and world soften and fade, consider this. You began this journey seeking understanding, seeking to comprehend the quantum realm, to grasp its principles, to make sense of its strangeness. And you've learned much. You've seen experiments. You've followed mathematics. You've confronted paradoxes. But has the universe become more comprehensible? Or has it become more mysterious? Perhaps understanding at this level is not about answers, but about deeper questions. Perhaps wisdom is not knowing, but knowing that you don't know. Perhaps enlightenment is not clarity, but comfort with uncertainty. The quantum realm is not a puzzle to be solved. It's a mirror to be looked into. And what you see in that mirror is not just the universe, it's yourself, the observer observing, consciousness becoming aware of consciousness, mind contemplating the nature of mind. Quantum mechanics is telling us something profound about existence, about the relationship between potential and actual, about the role of observation in creating reality, about the interconnectedness of all things, about the fundamental mystery at the heart of being. But it's not telling us in words. It's telling us in math, in experiments, in phenomena that defy verbal description. It's showing us that reality is deeper than language, stranger than stories, more mysterious than any explanation we could devise. And perhaps that's appropriate. Perhaps the deepest truths can't be spoken. Perhaps they can only be experienced, lived, surrendered to. Sleep is coming. You can feel it. Consciousness fading. Thoughts becoming dreamlike. The definite world dissolving into quantum indeterminacy. And perhaps sleep is the perfect metaphor for quantum reality. When you sleep, you exist in superposition. You're conscious and unconscious, dreaming and not dreaming, here and elsewhere. Your sense of self becomes fluid, indefinite, probabilistic. Dreams, the rules change, time flows backward. You're yourself and someone else simultaneously. Contradictions coexist. Logic dissolves. The classical world gives way to something quantum, where all possibilities are present, where observation creates experience, where consciousness is the only reality. And when you wake, the wave function collapses, the superposition resolves, you become definite again. Classical. A single self in a single world with a single history. But the quantum substrate remains. Underneath the appearance of solidity, the uncertainty persists, the superpositions continue. The entanglements endure. The deeper reality never went away. You just stopped perceiving it. Perhaps enlightenment is learning to perceive it again. To see the quantum nature of reality even while awake. To recognize that the definite world is appearance, and the quantum realm of infinite possibility is the truth. Or perhaps enlightenment is accepting that both are real, that reality has layers. That quantum and classical are both true, in different contexts, at different scales, for different purposes. Perhaps the goal is not to choose one view over another, but to hold both simultaneously, to live in superposition, to be both quantum and classical, both definite and indefinite, both certain and uncertain. And so we end where we began, with a question. Are you here? Are you real? Do you exist in a definite state or in superposition? The answer, if there is one, is both and neither, and something beyond both and neither that language cannot capture. You are a quantum system that has decohered into apparent classicality. You are a wave function that has collapsed into definite experience. You are a node of consciousness in a participatory universe, creating reality through the act of observation, entangled with everything that exists, emerging from quantum foam and returning to it, temporary and eternal, particular and universal, alone and connected, consciousness emerging from matter to contemplate matter, mind arising from the quantum realm to understand the quantum realm, the observer and the observed, unified and separated, distinct and entangled. This is what quantum mechanics reveals. Not just facts about particles and waves, not just predictions about experiments, but something deeper, something about the nature of existence itself. Something that cannot be fully known but can be intimately felt as you drift into sleep, as consciousness fades, as the quantum superposition of dreaming and not dreaming claims you. Rest in the mystery. Rest in the uncertainty. Rest in the profound recognition that reality is stranger, deeper, more mysterious than we ever imagined. The quantum realm has no bottom. The deeper you look, the stranger it becomes. The more you understand, the more you realize how little you understand. The questions multiply faster than the answers. And that's not a failure. That's not a gap in our knowledge that will someday be filled. That's the truth. That's reality. An infinite mystery, an eternal question, a bottomless depth of wonder and strangeness and beauty. You are that mystery. You are that question. You are quantum and classical, wave and particle, observer and observed, potential and actual, temporary and eternal. And tomorrow, when you wake, when consciousness returns, when the definite world reassembles itself around you, remember this journey. Remember what you've learned. Remember that beneath the appearance of solidity, the quantum realm persists, infinite and strange and beautiful. Remember that you are not separate from it. You are made of it. You are it. The quantum realm is not elsewhere. It's here. It's now. It's you. Sleep well, quantum being. Dream deeply. And know that in the morning, when the wave function collapses again, when you return to the classical world, the quantum mystery will still be there, waiting, infinite and eternal, beneath every surface, beyond every boundary, at the heart of every atom and every star. The universe is quantum, reality is uncertain, and you are the consciousness that observes it all, creating reality through observation, participating in the eternal dance of quantum collapse and quantum possibility. Rest now. The quantum foam from which you came awaits. The superposition beckons. The infinite possibilities call, and in the space between waking and sleeping, between definite and indefinite, between here and elsewhere, you touch the truth of what you are: quantum, eternal, infinite, real and unreal, both and neither, perfect in your uncertainty, complete in your incompleteness, one with the quantum realm that is all that exists and has ever existed and will ever exist. Sleep now, dream deeply, and dissolve into the infinite quantum ocean from which all reality emerges and to which all reality returns, forever and always. Quantum, eternal, one. Thank you for this journey into the quantum realm. May you rest well, and may the mysteries we've explored continue to whisper in your dreams.